Hello, this is Dr. James Camp from Lee College in Baytown, Texas, and this is my commentary on Chapter 1 of Big C++ by K. Horstmann. This is an introduction to computers and programming and C++ and just a little bit of algorithm design, so it's kind of a catch-all introduction chapter. Programming is the idea of designing and implementing computer programs. Most people think of programming solely as the act of sitting in front of a computer and writing code. And that may be the thing that you spend most of your time doing, but probably you'll spend more of your time debugging the code if that's your strategy. If you do a little bit more planning in advance, if you spend more time on the planning your program part of programming, you may find that you spend less time debugging and more time writing productive code. Okay, so let's talk about computers. Computers are used for everyday tasks such as reading your email, electronic banking, buying things on e-commerce websites, writing a term paper, doing budget calculations on a spreadsheet. Computers are really good for any kind of task that involves kind of repetitive chores, totaling up numbers, formatting words on a page. Computers never get bored. They never get exhausted. They never complain that you're having them do the same thing too many times. Computers are also good at doing all of the tasks, many of them kind of simultaneous tasks, involved in simulating a make-believe world, such as you may have seen in a video game. You may think of Minecraft, for example, as a really fun video game, but to a computer scientist, it's actually a really detailed and in-depth simulation of a virtual world. It's both, and it's the high-tech simulation of the virtual world that makes it such a fun and immersive video game. So computers can carry out such a wide range of tasks because computers are programmable. If you watched my previous video on my introduction to computers, you know that programmable was one of the features of the modern computer. A program, we didn't talk about what a program really was, though, in that lecture. A program is a set of instructions that tell the computer in very minute detail every step it needs to follow to perform a particular task, or often a set of tasks that are related in some way. The computer itself is a machine. We call it a machine. It's not a machine in the old-fashioned sense of something with gears and an engine and pulleys and all of those sorts of things. It's a machine in a computational sense. In fact, the organization, one of the two organizations that computer scientists tend to join as a professional computer scientist, is called the Association for Computing Machinery, or ACM. So the computer is a machine in a sense of something that does automated and repetitive work for us. And the kind of work it does, it stores data, numbers, text, media such as sound or video or images, and it gives us a way to find and retrieve that data once it's been stored. Obviously, it would be useless to store data if we didn't have a way to then find it and call it back up when we need it. A computer interacts with other devices. My computer sitting on my desk has a monitor, it has a keyboard, it has a mouse, it has a backup hard drive, and it has way off in another room a printer. It also has speakers and a webcam, so it's got lots of devices that it interacts with. And And finally, what we're most interested in this class is that a computer executes a wide variety of programs. You might use the same computer to balance your budget 1 minute and play a game to entertain you the next minute, and correspond by email or social media or whatever other communication app you have with someone across the world the next minute. Another way of looking at a computer, not just breaking down its tasks, is breaking down its components. Everything inside the physical box that you call a computer is hardware. And all of the physical devices that that box interacts with are also hardware. Okay? If it's physical, if you can pick it up and touch it, it's hardware. Software is what the computer runs. Okay, it's the instructions that tell the computer what to do. So the operating system that the computer boots up into and all of the programs that you install on your computer are software. We don't talk about programs much these days. We talk about apps. The word app has become common language because of Apple's App Store for the iPhone. And before that, Java had things called applets that could be run as part of a web page. But what app stands for actually is application software. Software that applies the capabilities of your computer in some way or another. And all of those apps, all of those programs, all of that, even the operating system that runs everything else on your computer are software. At the heart of every computer, hardware-wise, is something called a CPU, or Central Processing Unit. The textbook is old enough to say that this executes one operation at a time. I've added the phrase per core because nobody sells a single core processor anymore. Even the most simple processors that you buy from Intel or even in your cell phone are going to have multiple processing cores in them, at least two. So each core has the ability to execute one operation at a time. And computer processors in the last generation have kind of hit a speed limit of about 3 or 4 gigahertz. And so instead of trying to speed up the process, each operation, processor designers have just added more and more cores to the chip, which means that it can do 3 gigahertz times 4 operations at a time, or 6 operations at a time, or 8 operations at a time. What does the CPU do? It carries out arithmetic, so it can add and subtract and multiply and divide, and that's where the word computer comes from. It can also fetch data from memory or devices connected to the CPU, and it can store or push data back to the memory or the devices that are connected to it. It also handles program control, controlling flow of the program from one instruction to the next. This slide notes that all data travel through the CPU, and that is got a little asterisk after it, or I've added one, because if you study high-level or if you study highly detailed computer architecture, you learn that there are situations where input-output buses can be designed to bypass the CPU and save some time. That if you want to copy from one hard drive to another, there's a way to set up an automated system that just runs that copy operation off the CPU, so that you're not bogging down the computer. Not all computers have that ability, and in fact, it's probably pretty rare, but it is possible. So there you go. The computer stores data and programs in memory. There are probably several memory chips plugged into the main circuit board, sometimes called the motherboard or the main logic board of your computer. Most of those chips are random access memory, memory that can be read to or written to or read from, almost at the speed of the processor. Probably, an order of magnitude slower than that, but not very much slower than that. There's also something called read-only memory, which in modern computers is mostly used for the boot code. Sometimes they call it the BIOS, that gets your computer up and started when you turn it on, and handles how it talks to the most basic set of devices that plug into your computer, or in modern cases, that wireless into your computer. I put a star by the read-only memory as well, because these days read-only memory isn't actually read-only. Every now and then my computer alerts me that there's an update to my BIOS, and so I download a little patch and it rewrites the read-only memory. So obviously there's a mechanism, and we'll talk about that in another class on computer architecture. But there is obviously a mechanism for updating read-only memory, so it's not completely read-only. There are secondary storage devices then that the problem with random access memory is, while it is very, very fast, it is also volatile. Again, we talked about this in my last lecture on the introduction to computing. And so whenever you flip off the power to your computer, you lose everything in RAM. This is less of a problem if you have, say, a laptop with a battery, but even batteries run out of power at some point. So there has to be some kind of secondary storage device that can save information for longer periods of time. Historically, computers have had two kinds: non-removable and removable. A non-removable drive used to mean a hard disk drive, a little platter of metal CDs that whirled around at very high speed and were written to magnetically. Today, those are increasingly being replaced by solid-state drives, which are essentially like random access memory chips, but they preserve their state when they lose power, so they're persistent or non-volatile memory. Because they're essentially like memory chips, they run almost at the speed of memory, and so computers with a solid-state drive tend to be much, much faster than computers with a hard drive. Removable media is going the way of the dodo these days. Used to be that every computer except the most slim laptops would come with a CD or DVD drive that would let you write gigabytes of data to a little plastic disc, or plastic and metal disc, and then carry that around with you or use it as a backup or something. And it used to be that everybody carried around one of these USB flash sticks so that you could transfer files from one computer to another. Nowadays, those are going away for two reasons. One, most people that I know have a laptop, and so they carry their files around with them on the laptop rather than on a USB flash stick or on a CD. But also, most people are now taking advantage of some form of cloud storage. Microsoft installs its OneDrive software by default on every Windows computer. Apple does the same thing with its iCloud software. And I include a cute little cartoon here just to remind you that there is no such thing as a cloud. Okay, they're not this storage device that just floats up in the sky somewhere. It really is, you're paying someone else to store your files on their computer. And there are distinct advantages and disadvantages to this. The advantage is that it's someone else's expense that has to pay for maintaining that backup storage that you're using. You have to pay a subscription fee for it usually, but the fees tend to be pretty reasonable. On the other hand, it means that someone else could break into Microsoft's OneDrive server or Apple's iCloud or the private Dropbox server, and your stuff is suddenly compromised. Of course, that could happen if you have it on your private computer as well. It's just that nobody's really all that interested in breaking into your private computer. They're much more interested in breaking into a giant, big target. Okay. Input-output devices. Throughout this class, we're going to talk about how the user will interact with the programs you write. What is a user? A user is any human using a program that a programmer wrote. Okay, so in most of the cases that we program in this class, you're actually going to be the user for your own programs. I'm going to say, write a program that lets you keep lets the user keep a journal. Well, who's going to keep the journal? Probably you. You're probably not going to distribute this to all of your friends and have them keep journals with it. If you want to, you can. That would be pretty cool, but it's unlikely to happen to most of you. The user has two capabilities with the computer. They can enter information called input for the computer, and in this case, in this class, we're always going to use the keyboard for entering information. But as you get more into programming, you'll learn to access pointing devices such as a mouse or a touch screen, and you might even learn more advanced methods like accessing the computer's microphone or camera. And then the other capability of the user is that they can see information that is transmitted to them, see or hear, I guess. You've also got speakers on most computers. They can see output information, okay? Again, in this class, we're always going to be dealing with output as text on a console screen. But again, as you get more advanced in your programming life, you'll learn how to use graphical displays on a display screen like a Mac or Windows machine. You'll learn maybe how to play sounds through the computer speakers, or even how to send entire documents to the printer. Okay, other forms of input and output involve reading and writing to or from files. We will learn that. We'll actually learn a little bit about that in my first lab class. But we'll learn more about that throughout this class. More advanced than this class is going to get into then is reading and writing from network sources. So, for example, you might have a computer program that wants to know what the current weather conditions are. There are weather servers out there that you could send a request to, and it could send you information back. That's a form of input for your program. Okay. This is the anatomy of a computer. You can see that the computer, the CPU itself plugs into something called a bus, which is part of the main motherboard again. Information from the keyboard, for example, travels through usually a USB port onto the bus, and then it gets offloaded from the bus into the CPU. The CPU does whatever it's going to do with that input, and then let's say it wants to display a message on the monitor. It pushes information out to the bus until that information finds the graphics card, and then the graphics card interprets that information as, okay, you want to print this text on the monitor, and sends it to the screen. And then your textbook just wants to use this as an interesting point to mention. that we think about computers as relatively small devices these days. The very first fully functional Turing-complete computer was the INIAC at the University of Pennsylvania, which was developed for World War II. It was developed during World War II to calculate military projectile distances and pathways. The simple calculation that you can do for that you learn in Physics 101 for projectile motion doesn't really work so well when you're sending missiles from or rockets or shells or whatever from, say, one ship to another ship in the battle in the Pacific, where you're dealing with the curvature of the Earth and various other issues that those projectiles might have to deal with. So this machine was able to do those calculations, but it took a long time to program it because of the kind of complicated and wonky system that they used for doing that, switches and cables and all sorts of things. However, it was still much, much faster than doing the calculations by hand, and faster even than electromechanical calculators that had been developed prior to that moment. Okay, so now let's talk about programming itself. Computer programs, the ones that actually run on the processor, are stored as binary machine instructions in a code that is entirely specific to the processor type. So when I say processor type, there are currently x86 processors. Those are like the Intel Pentium or Core or the AMD Ryzen processors. There are also ARM advanced RISC machine processors like the ones in most cell phones and tablets. So a typical sequence of machine instructions might be fetch the contents of a memory location, move it into the CPU, check that value to see if it's greater than a signal value 100, and if so, jump to memory location 11280. This translates in x86 assembly or machine language into the following string of unintelligible numbers. Okay. On a processor of a different type, the encoding would be entirely different because the numbers of the instructions would be different. But in fact, the sequence of instructions might be entirely different. An ARM processor might not have you transfer the memory location and then if they're jump to this in exactly the same sequence that an x86 does. So assembly language programming is very, very or machine language programming is very, very processor specific. And in fact, it's even worse than that. It may be somewhat operating system specific as well, because accessing stuff from memory might involve getting the permission of the operating system. So there are operating system level issues as well. So just because you have, for example, if you have a program compiled for a Linux box running on a Pentium and a program compiled for a Windows box running on a Pentium, they won't run the same program. The same compiled program will not run on both. Okay. Because of this concern with machine language programs being so machine specific, high-level languages like C++ were invented. People wanted to write programs in a language that was closer to what we call natural language, which is how you and I speak. And they wanted to write programs that are independent of processor type and operating system, that the same code could be compiled on different processors and different operating systems. If a C++ program is written using the standard libraries instead of operating system-specific libraries, or processor-specific libraries, then the C++ program will work equally well on an x86 processor like a Pentium or on an ARM processor such as that found in most cell phones. If you can find a C++ compiler for your cell phone, which is less likely, but they're probably out there. High-level languages like C++ also tend to be standardized by international bodies such as the International Standards Organization and the American National Standards Institute to ensure that code written to that standard is going to be compatible across all compilers, all devices, all operating systems. In that respect, we can see that C++ has actually evolved over time. C itself, the language C++ is based on, arose in the early 1970s, but was not actually standardized until 1989. C++ arose in the early 1980s and was standardized in the late 1990s through about 2003. Prior to that, there were multiple competing C++s depending on what compiler you bought from who. In 2011, there was a major revision to C++ that added several important features that we will be covering in this class. The C++ that I teach you in this class will be C++ 11. There have been minor updates in 14, 17, and 20, but none of those have completely changed the landscape of C++ the way that 11 did. But I'm going to assume that in 2022, any compiler you're going to use is going to be at least C++ 11 compliant. So we're going to teach you the 11 version. Okay. The present C++ is commonly used for a few things. Database systems and operating systems, anything that's a real big system of software, C++ is great for writing. Embedded systems, so this time we're talking about a very small system, but a highly optimized system for running the computer parts of your car or of a smart appliance or something like that. The computer that runs your washing machine is probably programmed in C++. And then certain high-performance desktop software. C++ fell out of favor for desktop software for a while because of Java and C# and some of these other languages. But C++ has the ability to make direct interfaces with the hardware in ways that Java and C# don't. And so if you really need high performance out of your desktop software, and that might be a scientific software package, or it might be a video game that just wants really high performance graphics or something, those can still be written in C++ these days. Okay. As an aside, C++ is a compiled language. The major competing language in the world out there today, Python, is an interpreted language. Why would we go with a compiled language instead of an interpreted one? Or why might you want an interpreted one? In a compiled language, the compiler translates the high-level code, the human-readable code, into low-level machine language code ahead of time. Okay? Then when you're ready to run the program, the low-level code runs directly on the processor. In an interpreted language, the interpreter reads the high-level code one instruction at a time at runtime, while the program is running, and performs the appropriate action. You can imagine that that's going to be a little bit slower because the interpreter has to read and decode the instructions while the program is running. The disadvantage to a compiled program is that compiling itself takes some time. You will find that this varies depending on what kind of complexity of program you write and what kind of processor you're running on your computer. My i7 processor running the kind of programs or compiling the kind of programs that I write for this class takes almost no time to compile at all. An i3 processor trying to compile a several page or several file bit of code of C++ might take several minutes to compile. But the advantage is that once the programs are compiled, they run fast. Okay, they run at processor speed. The disadvantage to an interpreter is that interpreting is slower than running compiled code. Okay, the JavaScript that you run when you load a web page is interpreted. The Python that you sometimes get in the code behind a web page is interpreted, and those things run slower than the compiled code, and so you're going to end up with a little bit of a performance penalty. The main disadvantage to compiled code is that the compiled program is CPU and OS specific. So if you want to distribute compiled programs, you have to compile a Windows x86 version and a Windows ARM version and a Linux x86 version. In fact, you might have to write one for each different Linux that's out there, and a Mac x86 version and a Mac new M1 chip version. So you can quickly get into compiling 10 different versions of your program every time you make an update. On the other hand, interpreted scripts, we don't usually call them programs, we usually call them scripts, are often completely cross-platform. If they use the standard libraries entirely and don't tie to anything platform-specific, one JavaScript program can run on any web browser or on any computer that downloads it, whether it's a mobile phone or a Windows machine or a Mac or a Linux PC. Okay, so that kind of explains what a compiler is. It's a special computer program that translates your high-level language into machine instructions for one particular processor OS combination. You might have several compilers installed on your computer if you're really, developing cross-platform software. A low-level language then is the machine code for a specific CPU and often a specific OS. Okay, but the programmer who uses the compiler doesn't really need to worry about those issues unless you're really looking at distributing your software to lots of different people. Okay. So that's all we need to know about computers and the compiler and programming language theory. We're now going to talk about, writing your first program. Your first program, you're probably going to write in what's called an IDE, or Integrated Development Environment. Most of these look fairly similar. I believe this is the Eclipse IDE that's being shown here, but most of them have some sort of a project pane that shows the different components of your program, including at least one that ends with .cpp. And then most of them have in the middle of the screen a place where you can type and edit your code. You use that built-in editor window in the middle to type your C++ programs. Since what you're typing is known as source code, the file you're working on is called a source file. And a source file in C++ usually ends in .cpp, which stands for C++. Okay, you can compile and run your program in the IDE. Usually there's a single button that you need to click to both compile and run the program. In modern IDEs, it often looks like a little play icon, a little triangle pointing to the right. And then there's a debugger built into most IDEs that's very helpful for troubleshooting code. We'll explain how to use a debugger later in the class. Okay. The compiler follows the following kind of flowchart here to translate C++ programs into machine code. You use the editor to write your program, and that produces a source file here. Then the compiler translates that into machine code, which is no longer human readable. Your computer already has several library files installed with the compiler, and those are joined with the machine code that you just compiled by something called a linker. And the linker links all of these pieces together to create an executable program. And that executable program in an IDE then just gets immediately executed in a little console window so you can see your program running. Programming is not a linear process. You're going to write your program, you're going to hit compile, and you're going to get compile errors. This is inevitable. There have been a few cases in my life when I have written a program completely from start to finish without any compiler errors, but it's pretty darn rare, okay? And I don't expect it to happen at all to someone at your experience level. You're going to make some mistake somewhere in your syntax, okay? So you catch those compiler errors, you go back and edit the program again, and you fix the compiler errors one error at a time until there are no more errors, and then finally it's time to test the program with actual input. And generally speaking, again, this has happened to me a couple of times that I've never had that I have written a program that did exactly what I wanted without runtime errors, but it's pretty darn rare. You'll get a situation where the output does not match the input, or the output does not match what you expect from the input, I should say. And at that point, once again, you come all the way back up here to the edit program step, and you try to find the place where the error occurred. You fix that, you compile the program. Maybe that generates another compiler error. You fix that, you compile the program. You test the program with the same input and see if you fixed the problem. This is a loop that can take hours or days sometimes. So don't imagine that the time you spend writing the program is all the time you're going to have to spend on programming. Note that most IDEs today create what's called a project folder for each programming project that you start. These are buried somewhere on your hard drive. Microsoft Visual Studio recently has started putting everything in a your user folder slash source slash repos folder that's designed to be used with a repository system like GitHub. You may want to change that and have it saved to your documents library, such like the person here did in their in the example shown on the screen here, where you have in the documents folder you have a Visual Studio folder and then projects, and then the project is called foo for some reason. Be sure to back up your work frequently, okay? I can't emphasize enough how many times I have lost programs in the middle of writing them, and whether my day was ruined or not depended on whether I had been saving regularly along the way. One of the handy tricks for that is that every time you make a small change in your program, you save it, you compile it, you run it, you see what happened. And that way you've got a save point every time you've made one minor or major change. A handy way to automate being able to get backup copies is to save your project on a cloud drive such as OneDrive or Dropbox. OneDrive and Dropbox particularly save version histories. So you can go back and say, okay, at 3 o'clock today, I had the program running fine. Then I made a change and it's now 4 o'clock and the program won't even compile. Let me go back to the 3 o'clock version and start over again. Okay, you can do that with OneDrive or Dropbox. Another alternative is GitHub, which there's support for that's built into Visual Studio. I think it's also built into Apple's Xcode, but I haven't used it that way. GitHub's a bit more complicated than setting up OneDrive or Dropbox, so I'm not going to encourage that for you at this stage in your programming life. Finally, if none of those services work for you, you can just go about manually making a backup copy of your project folder every time you're about to make a major change. So maybe you get Hello World working and then you're about to go on to the next step. So you make a copy of that project folder and then you make the next change. Okay. I've got a separate video in which I go through the Hello World program with you, but for my first lab video, but I'm going to go through it here as well just to cover everything. The first line in most C++ programs is going to be at least one #include line. These include library files that provide specific sets of support code. C++ is so modular that it doesn't even include input-output code as part of the core language. So you need to source your input-output code from a library. So we're choosing to use the stream input-output in this class, so we'll always be #including IOStream in our programs. The next line of code, after all of your #includes are done, in most C++ programs is going to be using namespace std. That does not mean sexually transmitted disease. That means standard. Okay, and that means that you're using stuff from the standard library. C++ by default hides all of its standard library names in a standard std : namespace. And you'll see if you go through any of the documentation on c++.com that they use the std : syntax before all of the standard library stuff. We choose in this class to just tell the compiler that we're going to use the namespace standard and then leave the std : prefix off of things like cout and endline. Okay. The next set of code defines a function named main. Every C++ program must contain exactly one main function. You can't have two main functions and think that the compiler is going to pick one. You can't have no main functions or the program won't link and run. Main has to be of type int, and it has to have parentheses after it. There is something you can put in the parentheses to get command line arguments. For right now, we're just going to leave the parentheses empty. Okay. Braces, or curly brackets, sometimes they're called, must enclose all of the code that belongs to main. Okay, so the compiler will start with the first open curly there, and then everything it comes to until it gets to the closed curly, it's going to believe belongs to the main function. Now we're going to add more sets of curly braces to our code as we add things like if statements and while loops, and eventually we're even going to write our own functions that aren't main. To show output on the screen, we use the cout object. Okay, the things you want displayed on the screen are sent to the cout object using the less than operator, sometimes called the output or the insertion operator. Okay, so less than quote hello world means we're going to send the phrase hello world. We're going to send that string of text to cout. Then this curious keyword at the end, endl, means end of line. In old systems, it was expensive to send characters to the screen, so they would wait until they saw the end of a line, and then it would print all the information to the screen. So end line does two things. It ends a line of input, or of output, so that the screen knows to print it. and it moves the cursor down to the start of the next line so that you're ready to do more output. Note that you can display more than one thing by chaining less than operators. So you can say a big hello world end line, and it'll print the phrase a big hello world to the screen. Finally, the main function returns an integer, an int. That's why its type is int. And it's going to return the value 0. Again, kind of in the older days, the operating system looked for a return value from a program to know whether that program had exited successfully, in which case the error code would be 0, or whether there had been an error encountered, in which case there would be an actual number returned that meant something to the operating system. Okay, we've covered output statements, and it's worth noting that the word hello world, which is enclosed in double quotes, is called a string. Okay, and you have to put those double quotes around strings or they won't work. Okay. One last comment on proper C++ syntax. Each statement in C++ ends in a semicolon. Okay. The lines colored red below are statements. They cause C++ to do something. Okay. To set a namespace, to print output, to return a value. The black lines below, the pound include and the int main, are more defining. They're code that defines something rather than doing something. And so they're not statements, and they do not end in a semicolon. It's a little bit strange to figure out which things need a semicolon and which things don't, but you will get used to it as you go through it. Okay. Once we've written a program, we need to find the errors in it. Okay. Probably the most common error for beginners is to leave off a semicolon at the end of an output statement, or at the end of any kind of statement. Without that semicolon, C++ interprets your line as not having actually ended, and so it assumes that you wanted to send to output end line return 0, which is not proper C++ syntax. So you'll actually get an error on the word return 0 that will tell you that that's not legal at this point. It might tell you that there was a semicolon expected, but you then have to trace backward to find where the semicolon was missing. C++ compilers are not smart enough to give you the to put the error code always in the place where it would be most useful. Or suppose you wrote cout instead of cout. This will cause another compile time error. Undefined symbol COT or unknown identifier telling you that it doesn't know what cout means. Okay, it's not going to guess that you meant cout and say you misspelled cout. It's just going to tell you that it doesn't know what that means. Okay, when you get errors, the compiler generally does not stop compiling. It will keep going through the rest of your code, and one error may end up sparking several more errors before you get to the end of the program. As a general rule, it's best to fix only the first error that the compiler reports, and then recompile the program, rerun, see if you've fixed maybe several errors with one fix. Okay. A little advice. C++ ignores white space when it compiles. So it doesn't care whether you leave one line between cout hello world and return 0 or 3 lines or no lines. You can write your entire program as one line of code as shown here. But that makes it hard for you and other programmers who may come after you and try to use your program. Makes it hard for you all to read. Okay. So a good program spaces out your lines across multiple lines of code. Generally, one statement per line is the best rule. And we'll talk as we go through the class about how people tend to indent their code. As you've seen so far, the body of an int main is typically indented one level compared to the declaration int main. Okay, what if instead of hello world, we typed hello world? We're talking to something that's been mixed in a blender? I don't know. That's a logic error. We didn't do anything that's bad syntax, okay? We didn't do anything that the compiler will catch. We just made a mistake in writing the code. In this case, I just misspelled a word. But the program will compile, and it will execute, and the result will be wrong, okay? The programmer then has to step through the code and find the place where the error occurred and fix it. And that's probably the most laborious part of programming. Some kinds of runtime errors will not just give you wrong output, they will actually break the program. They will cause the program to crash, or in computer science terms, generate an exception. Okay. If you do integer division 1 divided by 0, the processor doesn't know how to do 1 divided by 0, so it's going to cause a divide by 0 exception and terminate your program. Okay. Some other common errors, extra main functions. You might misspell the main function. You might give main a capital letter. That is not allowed. C++ is case sensitive. Everything has to be typed in the case, usually lowercase, that it was intended to be in. So you can actually, if you want, create a capitalized main function, but it will not do anything unless you call it specifically, because the linker is looking for a lowercase main function as the place to start your program. Finally, we're going to talk about a little tip on software development. There's a saying among computer scientists that weeks of coding can save you from hours of planning. And this is true. I mean, I have had situations where I didn't plan out a program in advance, and I spent a long time coding and recoding and recoding, and finally realized that I had just made a planning error in my programming. Okay. And the reason for that is that every program is based on what we call an algorithm. Okay. An algorithm is like a recipe that you have to specify inputs and steps for processing and outputs. And once you define your algorithm, the computer is going to follow that algorithm exactly. So the software development process should follow the steps indicated by this little green flowchart here. You should try to understand the problem first. Okay, you should not sit down at the keyboard and just start coding. Well, I think they want me to do this. You should develop and describe an algorithm using flowcharts, pseudocode, some of the other program planning tools that are out there. You should walk through the algorithm by hand with some simple inputs and make sure that the output, that the process makes sense and that the output is correct. Then, once you know your algorithm is right, you can translate the algorithm into C++. You should not, at your stage in the programming process, be sitting down to the computer and typing out a program in C++ when you haven't developed the algorithm by hand somewhere else. You should always write an algorithm in words, pictures, or equations before trying to write any C++. And when you get stuck on a problem in this class, I may ask you, okay, what's your algorithm? What is your program trying to do here? And if you can't tell me what the program is trying to do in plain English, then you're probably not going to be able to tell me what it's supposed to do in C++ either. Okay, so I've explained pseudocode in my first lab video on planning programs, but we're going to go through real quickly what your book has to say about pseudocode. Algorithms described in pseudocode should be unambiguous. The instructions should be very precise about what to do at each step. They should be executable in that you should be able to sit down with a pen and paper and follow through every step in the algorithm. And they should terminate. They should have an end condition that makes the algorithm stop at some point, maybe several points, depending on what you might have different outputs. So consider a problem that you have the choice of buying two cars. One is more fuel efficient, the other is less expensive. Okay, let's assume that you don't care about the environment here and saving the world by being more fuel efficient. You just want to save money on your car. Well, then we still plan to keep the car for 10 years, and we plan to drive 15,000 miles a year at $4 per gallon. Of course, the gas price will go up, but so if we factor all of those things in, which car saves me the most money? Okay, a first step in algorithm design is determining your inputs and outputs. The inputs are purchase price 1 and fuel efficiency 1 for the first car, purchase price 2 and fuel efficiency 2 for the second car. Our output is simply which car costs less over this 10-year period. Well, how do we figure out which car costs less? We can break this down in sort of a mathematical language. Total cost is going to equal purchase price plus operating cost. Well, purchase price is given to us. Operating cost we have to figure out. Operating cost is going to be 10 times the annual fuel cost. We're not going to figure in things like oil changes and periodic maintenance. The annual fuel cost is price per gallon times the annual fuel consumed. Okay, so now we need to figure out the annual fuel consumed. Well, that's going to be your annual miles driven divided by your fuel efficiency. And that's where fuel efficiency finally comes in. Now we can take that breakdown and reverse the order and say, okay, annual fuel consumed is miles driven divided by fuel efficiency. Fuel cost is price per gallon times fuel consumed. Operating cost is 10 times fuel cost. And total cost is purchase price plus operating cost. So now we've gone through a little algorithm for figuring out the total cost. Then, if total cost 1 is less than total cost 2, then we choose car 1. Else we choose car 2. Okay, the first car is $25,000 purchase price, but it gets 50 miles to the gallon, which means the total cost ends up being $37,000. The second car, okay, costs $20,000 up front, but gets 30 miles per gallon, and so its total cost is actually a little bit more, $40,000. So total cost 1 is less than total cost 2. The algorithm has us choose the first car. Okay, so that's another view to algorithm design. And notice that we just designed the algorithm and tested the algorithm without writing a line of C++ code. You should be able to do this in this class, and you should practice doing this in this class before you start writing your C++ code. Okay, so it's time to take a programming break. I suggest you try writing a program that instead of saying hello world says hello to someone's specific name. Or you could try alternatively saying hello world in several different languages. Plug hello world into Google Translate and get a couple of different hola mundo and whatever. And then I'm going to give you an algorithm design assignment that will have you following the steps of algorithm design we just looked at to figure out a simple but interesting mathematical problem. All right, that's it for today. Thank you for your attention. Goodbye, good luck, and happy programming.